last session of the day on a Friday.
You kept the best for last, for sure.
Exactly. Yeah, so I'm Michael St. John. I work for Red Hat. I'm in the partner ecosystem team responsible for cross-run initiatives and doing a lot of work with Enterprise DB as of late. So I'll introduce, or I'll let Torsten.
I'm Torsten Steinbach. I'm from Enterprise DB, VP and Chief Architect for Analytics AI. And if you haven't heard about Enterprise DB, we are sort of the Postgres guys. So we are the biggest group of initial group of committers for open source Postgres, and we have a very versatile portfolio for enterprise Postgres, hence the name.
Yep. Cool. So, sorry, I have a build in there that I wasn't aware of. Just to kind of like set the stage or start the discussion. You know, one of the things that we look at, going out and talking with different customers or different organizations that are deploying applications, is really there's this big mix of infrastructure, different application styles, different ways that people are interacting with code development, right? So typically, if you think about it, there was no real strategy behind how people built out their infrastructure, right? They would start a particular project and they would go in and project managers would figure out what they need for infrastructure. So today you see a lot of things deployed on various types of architecture, whether it's bare metal, virtual machines, or some things are, we had this big movement to everything cloud first, to now people saying, well, some workloads make sense in the cloud, some things need to be repatriated back to on-prem, things being delivered at the edge now as well. And so we see these diverse types of architecture. We also see diverse ways of application development. We see a lot of traditional applications that are out there that's perhaps built in .NET or Java type deployments, or even things like COBOL or C++ out there. But we also see new types of applications coming in, microservices, applications and containers that are built with more of a GitOps approach, declarative approach versus an imperative approach to the code development. And then similarly with people and processes, we see people who are still working with waterfall or agile type deployments versus people who are now looking at more of the GitOps, CI/CD pipelines and things of that nature. I think what's really important out of this is, as we see people trying to be able to support all of these different modalities, how do you do that, and how do you take and progress things to more modern architecture while still being able to support some of these older applications and the way that they are developed, and as well keeping up with the talent. If you want to acquire new talent, new coders probably don't want to be stuck doing old types of code development because it's going to limit their career in the future. So how are you able to offer all of these different access modalities for new developers? And so one of the things we see is, in creating value, you really depend on being able to develop and deploy applications faster. And this is where we bring in Red Hat OpenShift, where we see more of the cloud native applications being developed, but also being able to support things like older types of applications, traditional applications in a VM that is supported on top of that platform. Bringing in AI and machine learning, all of these new intelligent applications that are being developed, as well as analytics, being able to bring that in and build it into pipelines, build it into the ability to use serverless, to take inferencing and then event-driven deployment and spawning off different applications in that architecture. Being able to use the Internet of Things, bringing in all of this data that typically we're only using about 2% of that data. So how do we take that and accelerate what we're doing more? And this innovation culture where, one of the things, like just sitting in a few of the sessions here this week, I've come across new projects that I didn't know existed. So it's this constant update of new tools, new modalities, new things that are coming out, new projects that are coming out. And so one of the things we look at is, in a Kubernetes type of environment, what types of things are being deployed? And certainly we see things like logging monitoring, data ingestion, cleansing, analytics, all of this stuff, all of the, what I consider like the data discovery, acquisition, and preparation in the whole support model or lifecycle model of an ML ops type of deployment. But also AI and ML software, databases and data cache, and I highlighted those because it really talks to a lot of what we're doing with enterprise DB. And then I always love this slide because it kind of brings up a lot of the projects that we work on. And kind of ask yourself, well, why is OpenShift? Why am I talking about OpenShift? Why is that important? It's just Kubernetes, right? Well, but it's not. Yeah, Kubernetes is just that orchestration layer for containers. But then you have things like Argo CD for GitOps, or you have to bring in things like monitoring and metrics, and you have Prometheus and you have Grafana in there, and Knative for serverless. Just picking out a few here on the screen. You need all of those tools in order for all of this stuff to work together. And so what OpenShift does is it brings that base platform, that base orchestration platform for containers with Kubernetes, but then it expands on that by bringing in all of these other tools that you can use, and it brings it in and manages it and maintains it over time so that you have one platform that's supportable and enterprise grade going forward. So I talked a little bit about OpenShift, support for existing containerized applications as well as those applications now. We see this a big move this year, especially those traditional apps living in virtual machines being lifted and shifted into KubeVirt or OpenShift virtualization in our case. And that the ability to run those applications at the same time within the same platform and infrastructure gives you that seamless deployment across different infrastructures. So whether it's at the cloud, on a public cloud or private cloud, or whether it's on-prem or out at the edge. And then those self-service capabilities, automation that we build into the platform, and then being able to deploy that out in a secure, containerized environment. Okay, so kind of fast forwarding a little bit to Red Hat's AI portfolio structure, we have a number of things that we're looking at. And I mean, if you think about it, really, what Red Hat does, we are a platform company, platform and automation company, right? So if you look at AI models, a lot of that foundational model development we bring in to RHEL AI. And this is where we do that base model development, a lot of the tuning, the methodologies and tools that we use within that environment to build those foundational models. It also gives you the ability to have images that you are able to deploy. And then once you have that base model development, what OpenShift AI does, and I remember being here years ago with the old ODH team, the Open Data Hub team, where we were doing a lot of the workshops and such for what has become OpenShift AI. And this is really, if you think about it, taking a platform, the OpenShift platform that was really developed for DevSecOps, and then expanding that to more of an MLOps model. So being able to support a lot of the development or the ability for data scientists to work together collaboratively, and then building those models over time and that model life cycle so that you're able to support that and then scale those models and deploy them in production. Then we have the Lightspeed portfolio that really allows you to do it takes some of the AI inferencing and allows you to do more of the code generation, a lot of the automation that's within that platform, and then AI workload support, which allows you to do more of that lifecycle management over time. And then all of this is built upon our core platform, so Red Hat Enterprise Linux, OpenShift, and the Ansible platform. But there's a lot of areas there where either we have some things that we've developed into those solutions that might not fill all of the gaps, or might not even fit any of the gaps that we have in the overall platform. And so that's where we really rely on our partner ecosystem so that they bring in their core competencies to what we're working on together. Red Hat Enterprise Linux AI, or RHEL AI, based on, first of all, building upon what we were working with IBM Labs around Granite family of models, where we build LLM models. And if you typically think about it, if you go out there and you do a search on something like container storage, for example, you're going to get a lot of examples of how you keep your Rice Krispies from getting stale, right? When what you're really looking for is something to do with storage, persistent storage for an application running in a container. Well, these LLM models will allow you to do more of that granular type of model development that's more specific to your industry or specific to your company. And then we have a tool, InstructLab, that allows you to help build out those models over time. I'm going to move on to OpenShift AI, where we then take those foundational models, bring it in, we do that model development as I talked about, and then we build in that lifecycle, that full end-to-end lifecycle management. And that kind of brings us to EDB. So a couple of things I'll leave you with here before Torsten gets into the very particulars about all of this. But one of the things is we work with Postgres from an OLTP perspective. And you might ask yourself, well, why EDB? Why not just regular Postgres? Well, there's a lot of things that we build in with EDB, and I think Torsten already mentioned that they're the major contributor to the Postgres upstream project. Well, that has a lot of implications because they understand a lot of what customers are asking for, what they're trying to do, what issues they may run into that they build then into the code. But beyond that, there's also additional things like the scalability and resiliency that we test and we build in together with EDB and our platforms. That, in addition to additional tools like being able to integrate back with Oracle databases, which is important when you have a lot of these traditional applications that I referred to before that might be running in the same systems as some of these new applications that you're developing. There's a brief out there if you want to download that. We are also working on a couple of reference architectures that will be a little bit more technical depth around those things. And then another area that we're working with EDB on is around analytics and AI. One of the things that I work on is validated patterns. And we've created a number of validated patterns. One of the new patterns that we've developed is around LLM and RAG. And in that model, we use EDB as a PG vector or vector database within that model. We're working together now to expand that validated pattern into some more of the use cases that customers are looking for from LLM and RAG models. But if you'd like to take a look at the validated pattern as it exists today, it's there. Our reb.ht/edb-pattern. If you'd like to join us as well, we have a validated pattern SIG that we do through OpenShift Commons. So please join the Slack channel, join us for some of the meetings that we have. We have a call every 2 weeks, and we will have a breakout session at Commons in Salt Lake City coming up at KubeCon. So with that, I'm going to turn it over to Torsten to have a little bit more conversation and the depth.
Yes, so you've already seen some of the use cases where Postgres might play an important role for AI, but also outside of AI workloads. So why Postgres? Why are we talking about Postgres here at all? Well, because it's the best database since sliced bread. And I'm not joking, because if you look at what the others are saying, you don't have to believe me, you'll find very consistently that Postgres always comes out top in terms of popularity. Like this is a survey, an annual survey from database engines, and if you look at Stack Overflow, they also do developer surveys, so there's a developer perspective, very reliably Postgres comes on top. But how do we now talk about Postgres here in the context of OpenShift? Why OpenShift is or uses Kubernetes as we have seen. So it provides cloud native deployment architecture. One of the things that we have also done at ADB is we have launched an open source operator. And this open source operator really is working at the highest standard, so level 5 autopilot standard of operator. So totally autonomous. We open sourced it, as I said, so you can just use it for free, even though we of course have commercial support for that as well, for enterprise settings. It supports all kind of installation models, like manifest, Helm-chart, and so on. And it in fact has, in a short period of time it is there, has quickly become the most popular, largest growing operator. So maybe I can skip that slide here. So if you, this red curve, that's the start curve of this operator compared to other operators that were there before. So why is that? Well, because it's really very consequently using the best practices of how you should build an operator. It has been enabled, this whole thing took off with the advent of persistent volume claims, because this was the point in time when Kubernetes itself became ready for stateful workloads, and how more stateful can it be than the database. So, and this, the Kubernetes API, very consequently, using the operator pattern, and leveraging Kubernetes resources, standard resources for all of the configuration. That enables us, or enables you as a user, to be entirely declarative in interacting with that system. So you just define what you want, and we'll see in a second how it looks like, and then the state machine just goes off and does it for you, make sure it basically will always adhere to your definition that you want, the setup of the Postgres that you want. It has fully built-in observability for logs, for metrics, and so on, in order to enable such an autopilot mechanism at all. And it has a lot of provisions for security, that out of the box you can be sure that things like mutual TLS or so are always set up and used as operator. Now, as I said, everything using that operator is achieved declaratively. So what does it mean? Well, the declaration looks something like this. So this is now such a YAML file that you specify. I don't know if you can see from the back, but it's really pretty straightforward. You just say, I want to have a cluster resource of the type and of the image, Postgres image, and then you specify, okay, I want to have a cluster of 3, and one of this should be always a synchronous replica. The other can be asynchronous. So, and then you just specify, okay, the amount of storage for the persistent volume claims, for the main data, and for the wall storage. Wall is stands for wide head log. If you know databases, transactional databases, there's also some concept for transaction logs. In Postgres, they are called write ahead logs. So whenever you read that, it's a transaction log. And now let's look at this for different use cases. For instance, high availability. How can you achieve high availability with that simple declaration? What do we do to set up a highly available environment. Well, first of all, there's a Kubernetes cluster, obviously, and we leverage the concept of availability zones. If you have a cross-availability zone Kubernetes cluster, and we set up in each of those availability zones a worker node, and on these worker nodes, we deploy, first of all, persistent volume claims, one for the logs, one for the main storage, and of course the actual worker node itself, the worker for Postgres worker. So that's, and on top of that, set up a read-write service, so that's the external interface that the application now uses to talk to this Postgres database, to read and write, send read and write transactions. In addition, automatically, redundancy is set up here by setting up the whole thing on another node with a follower, synchronous follower standby, and another one because they said we just need one synchronous. Okay, this can be asynchronous. And then on top of that, we also set up a read-only service, and that means you cannot write to these. You cannot do insert updates and needs in these nodes, but when you have just read-only, reporting transactions, you don't have to basically put all this node on your primary. You can just spray that over the standbys here. Right? So you can leverage these resources. They are not just wasted just in case some failure was needed. You can really use them. And with that, we can enable HA with very low recovery time objective, RTO. Recovery time objective means the time needed to fail over. Because there's a fully working standby synchronously available all the time. And if this thing goes offline, the operator takes care that automatically the follower is promoted to the standby. Right? This external service is now rerouted to the standby, to this, makes this the primary. Everything continues to work. At some point, the first one comes back again, and the operator avoids a split brain situation by saying, okay, you're now not the primary anymore. But it demotes it to a follower and makes it not a synchronous follower. So that's all what you need to do is to write XAML file to get this behavior. Let's look at another aspect of availability. Let's look at backup and recovery. That brings us more into things like also disaster recovery scenarios. When entire sites go down, how can you recover from these kind of failures? So the first thing you need to see that one of the features we have in Postgres, and the operator fully exploits that, is a thing we call continuous backup. Continuous backup consists of the logs that are automatically archived every 5 minutes to object storage, and the periodic backup that is being taken. The combination of both enables us to always basically recover to any point in time. So basically it looks like this. We have the Postgres cluster somewhere, so just the thing we saw before, that's one big green box. And there's just the right ahead log archive, and the backup catalog being created automatically. That's your continuous backup. So that's also set up for you automatically. And how does the recovery work with that? Right? So recovery, what I mean with recovery now is really a restore. Basically, when you're bootstrapping an entire new environment from that persisted continuous backup. And you can have a full recovery. Full recovery means really you recover to the latest log transaction that has been written to this continuous backup. But you can also have point-in-time recovery. And this is for recovering logical errors, for instance. Right? You have done a mistake, you deleted some data. How do you get back? Well, this is a method to get back. Just restore the backup, the continuous backup, and recover just before this point in time. And basically, yeah, it basically looks like this. The backup is first restored, the logs are then applied, and then this new system is now a full copy. Right? It's promoted to be a full database. It's now from this point on independent, you can use it. You can use it also, for instance, you want to do some tests. Right? You want to have a copy of your system restored somewhere to do some test development, or to do some expensive reporting that you don't want to send to the reporting queries to our original cluster and things like that. What you also can do with that is now set up for disaster recovery, DR. And it looks like this, that you just do exactly the same. You set up a new cluster, the so-called, we call it now replica cluster, but you don't promote it. Instead, you continuously apply all of the new logs that are arriving in the archive. You just continue to do that. It means this replica cluster will always be running these same transactions as the original system. It will always be up to date, so that it can take over in case of failures. What it also can do is not just use it for failure, but you can also use this cluster to send your read-only queries to. But because it will be always up to date, it can serve queries, you can't do instance updates, but you can also leverage these resources. They are not just wasted by sitting around and waiting for the case of failure. Okay, and this is how it looks basically in a bigger setup here. You have these two things running side by side. There's at most 5 minutes, because this is this interval, we are writing archives, logs to the archive behind. And you can even improve that by saying, on top of that, I can optionally set up a real-time streaming apply here, so you're not relying on the write-ahead log archive, but really to stream over the logs as soon as they are, the transactions as soon as they happen. In a bigger setting here, it looks like this, right? So this is now the big picture here, broken down all of the individual components here. The cluster consists of multiple availability zones, all of the setup here. So it basically has a fully working setup here. That's why we call it a symmetric cluster. And in the case of a failover, it can immediately take over all of the work. There's no basically things that are lost here. Okay, and even this cross-cluster high availability for disaster recovery scenarios just looks like that. And it's just a set of declarative input that you provide in a YAML file, and the operator does it for you. So that's why this is a very popular operator that significantly simplifies enterprise setups with Postgres in Kubernetes environments. Okay, I want to end today with a more deeper dive into the AI side of things. And when we talk about AI and AI solutions with Postgres and OpenShift, let's talk about the AI first. Conceptually, what is intelligence, if you break it down, means you need a brain that can process things, that can make decisions, can have ideas, associations. We need some consciousness that drives things forward, that sets objectives and goals, and coordinates the steps. But you also need memory. But you need actual memory of things, experience, and so on. And if you map that now to artificial intelligence, you can very nicely map that. You have the brain, which is now in AI world, these models, or in a generative AI world, the LLMs. That's basically the thing that can make decisions and generate new ideas and so on. There's the consciousness, which is your application, your solution code that you're writing. This is basically coordinating the steps that you want to do. And what's the memory? That's the data. That's the data. It's a database, data warehouse, data lake, whatever, but it's data. And also you can sort of conceptually map that. This is something like Postgres, and this is basically OpenShift, where you have your solutions, and this is OpenShift AI, where you can host LLMs and run them for orchestration. A simple but very typical application that nowadays everybody's talking about GenAI or chatbots. How does it look like here? Well, you see the symbols here. The application logic is the things that is driving, that orchestrating these steps. And then we have some models, and then we have some data. So the first thing that happens is sort of the preparation that happens in the background. That's not happening when the user logs on, but it's happening all the time. I first need to store some data for AI in some database, data warehouse, and then you make it retrievable for these chatbots. And that's where these vector databases come in. And vector databases need something else. They need something that can compute vectors. This is now modeling in LLM, so embedding model. So the first thing that happens when you basically do that, these LLMs are run to take the data that you have stored here and process it in vector and put it in the vector database. So that's preparation. Now at runtime, the user comes in and says, oh, I want to chat. Send a chat message. The application now, chat application, sends it to the backend. The first thing that it does, it sends it to the same LLM computer vector for this chat message. And with this vector, a vector database lookup is done. The relevant similar documents are found and retrieved from the storage. And this is now the retrieval part. And now this data is now augmented to this chat message. So it's extended, you append it to this chat message and sent to this generation model. So this could be something like GPT, right? GPT-3.5, 4, Llama 2, whatever these famous models are there. And then this model can generate an educated response. Right? And this is how you avoid hallucination, because when you ask a model something that the model hasn't been trained with, this is the way to get the knowledge into the model on the fly, using this retrieval augmented generation or RAG. That's a RAG pattern. Okay, that's one thing that you need to be the functional side of AI stacks. But let's say you have built that somehow, and it's good. People love it, right? And you have the chat online warm when people come and use it, and they bring more questions, more data. Say, okay, can I use it for this or that? Okay, so you bring more data into your system. This RAG system becomes bigger and bigger, and they start to use it routinely because it's so good. You did a good job. Right? So it becomes, over time, mission critical because people rely on it. Have you thought about that when you build that thing? What does it mean that this is now mission critical? Right? Do you have a plan to make it really operational, sustainably, 24/7, supported, scaling with new user demands? But if you have a surge of users, that's something you need to keep in mind when we talk about AI in an enterprise setting. Right? And we're talking about that today here with OpenShift in Enterprise DB. We're thinking about enterprise customers and their requirements. Operationalization of AI needs to be thought about. And what does it mean, operationalization? Well, it means a lot of criteria. It needs to be always on, right? Operational quality. Things like, it shouldn't have a downtime necessarily. How can I have zero planned downtime? How can I be resilient against failures of my infrastructure? How can I be secure encrypting my data, so make sure that when I do a RAG pattern, it doesn't look up things that this user is not allowed to see. So you need to have fine-tuned access control and so on. You need to be responsive SLAs when have a minimum response time, even though more users come on. How do you do that? Scaling with the user. Enterprise support. Have a big ecosystem that you can basically rely on in terms of developers that you can hire to maintain the system. Connected to your existing business data and business events, transactions that are happening all the time. How do you make sure that all of this data is up to date in your system? Those are all operational qualities of service that Postgres has decades of maturity. That's why we are convinced that we have a very good shot here at Enterprise DB to become an AI database platform for such solutions. In combination, this looks like this. It's OpenShift, right, in Red Hat. You can look at it simply like this. There is the OpenShift Cloud Native Runtime. It's a platform you've heard about. You have the Cloud Native AI Data Management layer. That's Postgres. And you have a Cloud Native AI Processing layer and tooling layer. That's OpenShift AI. Okay, so that's what I want to leave you with. And maybe take away also this last slide if you want to follow up. Some of these links you have already seen before, like the solution brief here. We have the validated pattern, but we also have from EDB, we have pulled together a lot of these things into a nice webinar, and also into a tech preview that basically shows you the next generation AI database based on Postgres. Okay, so thank you very much. That has been our talk. Any questions?
So basic question about some data consistency, about synchronization, and also your continuous backup. So for synchronization, what's like the acceptable latency that to provide consistency that acceptable? And then for the continuous backup, like 5 minute, 5 minute losing could happen. And why not like default to streaming other than the write-ahead log, like 5 minutes backup? So.
Yeah, I mean, a continuous backup, to start with that, this is basically the basis for really recovering from scratch, bootstrapping from scratch. And then you it's for disaster scenarios and so on. I've shown you, maybe I didn't emphasize it, you can of course use other options. You don't have to entirely rely on this continuous recovery that basically can be at most 5 minutes behind, like you said. But you can set up transaction log shipping and replication directly from the original cluster to the DR, to the replication cluster. So you can do that. To basically, of course, you do not want to have a remote cluster that is on the other side of the continent to be asynchronous, because that basically will significantly slow down to the network latency of the original one. But you can set it up asynchronous, which means you have at most some seconds of data loss and not 5 minutes at most with this. Does that address it?
Thanks for the presentations. Because I have the scenarios that where we use the large language model for generating the YAML code. I wonder, can I use a RAG in that process for?
Yes, I would say generally yes. It depends on, of course, to use the right model here. But I mean, either you basically can take one of the code generation models, there are increasing options available, also tuned for certain languages, like also YAML, it's a programming language, code generation models. But even if it's not fine-tuned, I mean, we talked about REL AI, that's exactly the tool that we can say, use that to do the fine-tuning. But if you have a very specific language, or maybe a specific domain-specific language that you want to really be catered for in your YAML syntax, then I would say to fine-tune, take one of those code generation models and run a fine-tuning with it.
Yeah, I actually tried the RAG before. Because besides the fine-tuned model, I also have a large corpus that for RAG to reference into, right? Because for it to retrieve the data from, it turns out that when I combine it, I generate something like it's the concatenation of both the model generate the YAML and the content that the RAG retrieved from large corpuses. It's kind of the format losses in the sense that, well, the model can generate the YAML content, the format conforms to YAML, but the content that retrieved by the RAG, it's kind of a context. Then when we concatenate together, you can imagine how.
Yeah, I think maybe I should precisely when I said fine-tuning, of course there are two options. One is really you spend all of the fine-tuning of your code generation model. When you would on the basically actually use RAG, you should be spending time on fine-tuning your embedding model. So your retrieval is much more important. Right? To find that the embedding model generates vector embeddings from your example RAGs that you example YAMLs. Then you have the YAMLs that you basically have from previous projects. This is your data, knowledge. And these are the things that you need basically augment in the RAG flow. And in order to make a good lookup here, it can a good retrieval, it can mean that you may want to fine-tune the embedding model so that the similarity search is much more precise, basically find the right YAMLs that are best example for a certain question you send in a prompt.
Oh, that's a very good thing. You mean make embedding for the YAML, for the example YAML.
Yes.
And use the example YAML for the similarity search.
Yes. Yes.
And the RAG will retrieve the.
Yes.
kind of from the embedding instead of from embedding, so that we can get the kind of similar content.
Exactly, yes. I think maybe let me also just generalize it. That's a whole thing about RAG overall, why RAG is so popular, everybody talks about it, because it allows you to get to very precise generation, if you do a good job, without having to spend a lot of time and effort and money, frankly, to put into fine-tuning of the actual generation model, which is basically something, it needs GPUs, then you have a stale model that you need to, retraining takes hours. So RAG is the way to be much more dynamic and to the point.
Actually, we're out of time and we have a wrap-up session here, so any more discussion should maybe be hallway discussions.
Thank you very much. Questions, and we are here for more.
Yeah.